So before we actually get to related rates, I want to review implicit differentiation because that is what we use in this whole lesson in related rates. So in the past we did like d dx of both sides. So just real quickly, let's say I had x squared plus y squared equals 5, just as an example. So if I did d dx,
So stupid.
so you need to take d dx of both sides. So whenever it was an x, we just took the derivative like normal, so it would just be 2x. But what happened when we had something with a different variable? So if it's y squared, it would be 2y. Good, 2y dy dx. And then of course, a constant will still be 0. No. Okay. Okay.
Wait, can you go up a little bit?
It's just like, wait, can you get down?
Thanks. Now, can you go down a little bit?
Don't laugh.
Now, the thing that in the related rates,
Encourages him.
we may be solving for the dy dx part, or we might be solving for the x or the y or some other variable. So what I want to do with related rates, the key here is they are derivatives with respect to time. So related rates will always be d dt. So no longer d dx. So some of you asked, well, why is the x important? Because we were differentiating with respect to that variable. Now we're going to differentiate with respect to time. So every variable is going to have like a dx dt, dy dt, dz dt, or whatever the variable might be. Okay. Yes, a lot of dt's.
So when does this apply?
We'll get there. Related rates, like velocity and things like that. Okay. So 2x. So it's going to be, what would be the derivative? Just think about what would be the derivative of 2x. It would just be 2. But then we need dx dt. So remember, we're taking d dt of both sides. Yeah, just do the, like, think about what the derivative would normally be, and then multiply by dx dt. So let's do the same thing for the y squared. So just think, what would be the derivative of y squared? It would be 2y. Good, dy dt. And then we get equals, that's just going to be 0. Okay, we're not going to solve for anything because we have, so related rates means we usually have two different rates. This means this is the change in x with respect to time. It could be seconds, it could be hours, whatever. This is the change in y with respect to time.
Why don't you just get?
We're just practicing implicit differentiation. We'll solve in the next part. I wanted to back up and do just a couple examples so we knew how to solve it when we got there.
I have a hard time with implicit differentiation when it's just two lines.
Okay, so let's take d dt of both sides here. So think about just sine of y. What would be the derivative of sine? Okay, so it's going to be cosine of y, and then our variable is y, so we put times dy dt. Next, we have x to the third, so our derivative would be 3x squared dx dt minus 1 dx dt. Now here, if we ever have this in a particular problem, we could factor out the dx dt, so we only see it once. So it would look like this. And then we'd have 3x squared minus 1, just if we had to simplify that. We usually won't encounter that, but I just wanted to show that. Okay, so related rates, derivative with respect to time. That was just a preview so that when we get to the actual problem, you know how to take the derivative.
Yeah, it's already difficult.
The difficult part is kind of like optimization. The hardest part is basically steps 1 and 2. Step 1 is understanding the problem. And step 2 is developing the model for the problem. Basically, setting it up and relating. The first 3 steps are the hard part. Setting it up, after you have it set up, it's easy. It's take the derivative, plug in all your values. Luke?
Are these able to be graphed?
Yeah. It depends. We'll look. Okay. Let's go through some examples. It'll make sense when we see the examples. So obviously, number 1, understand the problem. That sounds like it. You know, with word problems, that's like kind of hard to do sometimes.
There's a lot of reading.
We have to draw pictures, label the parts. Okay. We also have constant quantities, like things that aren't going to change. Okay. For example, we have a problem where there's a ladder sliding, like a ladder that falls. The length of the ladder isn't going to change. Okay, so that's a constant value. Write an equation, this is the big one, relating the variables whose rate of change you seek. Okay, then you're going to differentiate and then substitute values. What's that? Question?
I just simulate process. Draw picture.
So, I added this to the notes. I don't know if this helps, but let me just show you some of the notation that we're going to be using. So we already saw like dx dt and dy dt. So just remember, this is the change, and so dx, think of x as a horizontal distance with respect to time. So the sample units would be like inches per second, meters per minute, feet per second would be an answer. dy dt also a change, that would be a change in vertical distance. We might have dz dt, might have a change in the radius. These are all measures. A lot of times we're going to work with something geometric. So dA dt, this would be a change in area, so that your units would be like square centimeters per hour. Again, these are just samples. Surface area, volume. Volume would be cubic units per time. So, as I just mentioned, we talked about, mentioned a ladder. Okay, so a ladder is slipping down a vertical wall. Can you kind of picture that? Prop the ladder up and it falls down. So, the ladder, the bottom of the ladder is sliding out and the top is falling down. Okay. All right, so let's first, so we understand the problem, okay? We understand what's going on. Now what we want to do is, the picture's already provided for us. We want to label the picture. Let's use, this will be x and this will be y. The ladder is 13 feet. So this 13 feet, this is constant. The ladder's not changing size. Okay, it's 13 feet, it's not getting bigger or smaller.
It might be one of those letters that you can change that.
Yeah, it could be, but it's not. All right, top of it is slipping at the constant rate at 2 feet per second. Okay, so what I like to do is go through the problem and kind of figure out what are we given. We're given that it's, the top is sliding down, so the top of it. So that means it's going down. That's a dy dt. And when it's going down, it's going to be a -2 feet per second.
Wait.
Okay. It's the change in y with respect to time. Do you see how it's per unit of time? Anytime you see like per second, per minute, that's going to be dt on the bottom. It's the change. The top, we said, was going to be y. So the change in y with respect to time is -2. We do. We know the change in y with respect to time is -2.
What's just the change in y on its own?
I just realized I'm missing another piece of information.
Yeah, because we don't know the.
Hold on.
There's no question.
Hold on.
I was gonna say that.
Yeah, the top is slipping down at the constant rate of 2 feet per second when, yeah, I'm missing like the rest of the problem. That's weird.
So what is it, flat on in terms of the ground or something, or?
That's, when the ladder, sorry, I have to add a couple, I must have, I copied and pasted this, but it didn't copy it, everything. So, the ladder is 13 feet. So, well, 12 feet is pretty far out, but that's okay. So when the ladder is 12 feet from the building,
One is
let me
the
change
ladder?
this, let me
Like,
change
say-
this.
Or that's,
Let me change this to 8.
One is the ladder?
When the ladder, no, okay, the ladder is 13 feet long, and the top of the ladder is slipping at the constant rate of 2 feet per second when the ladder is 8 feet from the building. So basically when x equals 8.
wait, but it's a constant rate?
No, hold on. It's slipping, it's falling down here at 2 feet per second,
Mm-hmm.
okay? So it's not like speeding up or anything.
So why does the distance?
So I wanna know,
Oh, is it the initial?
hold on. I wanna find out what rate is the horizontal distance changing? It would have helped if I had the problem all written out, but. So what rate is the horizontal distance changing? So I'm trying to find dx dt. So the ladder's falling down this way, it's going out this way, so I wanna figure out how fast is the ladder going out.
So what's the significance of the value of e for x? Is that the initial position of the ladder before
Yeah.
it started to fall? Oh.
Okay, so what relates these three measures? This looks like what kind of triangle? Right triangle. And how can we relate x, y, and 13? Pythagorean theorem. So x squared plus y squared equals 13 squared. Now, we want to write out the equation first, and then we're going to take the derivative with respect to time. So I want to take d dt of both sides. Okay, so what happens when we do the derivative of x squared? It becomes 2x dx dt. And what about y squared? It's going to become 2y dy dt. And what about the right side? 0. Okay, so I have to now plug in all the missing pieces. So I already told you I should have given you information about what x was. So I told you we're going to say x is 8 feet. So we're going to say this is when x is 8 feet. So 2 times 8, dx dt is what we're solving for. Now, y. I didn't give you a value for y. I only gave you a value for x. But if we know the triangle is 13 here and 8 here, could we figure out what y is using Pythagorean theorem? So go ahead and figure out what y is equal to.
It's the square root of 105.
What is it? 105, square root of 1.5? So we can put that in here. So once we plug all of the information in, we should only have one unknown. Okay, we only have one equation, so we have one unknown. So multiply this out, add it to the other side, divide by 16, and we should get our answer.
Oh, where'd you get the -2 from?
Yeah.
Okay, so it's slipping at the constant rate of 2 feet per second. So that's when we have rate, just like velocity, we could have when something's going in the positive direction, it's going to be positive. When it's negative, like falling down, going negative direction, going to the left, then we're going to put a negative in front. Anybody with a calculator? Okay.
Wait, I got lost. Why did we take the derivative in the first place?
So always take the derivative. So we want to find dx dt.
Okay, the whole point with related rates is that we're taking the derivative with respect to time, because this was a negative here. So when I moved it over, it became positive. So 4 times square root of 105 divided by 16. What do we get?
Okay, so.
4 root 105.
105.
It's just 105 divided by
That's
square root of 105 divided by 4.
2.
What?
Okay. What did we get?
2.562.
2.562. Perfect. And this will be feet per second.
Love.
So the ladder is sliding outward at a rate of 2.562 feet per second. So as the top is falling down, so here's the whole idea about related rates. The rate depends on a lot of things. It depends on not only the rate that we were provided with, but at different periods of time, like when x is 8, dx dt is going to be something different than when it's 10, possibly. Okay? So, like as something slides down, maybe this is going to start sliding faster. No? Yes? Question?
Just a random
Matthew?
question. For dz dt, is that just like the
dz. Okay, so sometimes this distance is also changing, but because it was constant, we were able to plug that in right away. So we plugged in basically, like there is a problem that we will have where all 3 parts are changing. Okay. I tried to simplify this over past years, and sometimes it doesn't work and sometimes it works. When I try to simplify it, sometimes I make it more complicated.
Say spherical balloon, like how balloon is
Well, some balloons are more like an oval
that?
type shape. So let's say we have a perfect spherical balloon, okay? It's inflated with helium at the rate of 20 cubic centimeters per second. Okay, so remember that table I gave you? Do you see how this one here has cubic? I know right away that's dv dt that they provided to us. Do you see that? This is dv dt because of the cube. Cube is always going to be change in volume.
So that's easy. That's one easy part.
That's one easy part.
The only easy part.
Okay. All right,
You
so
just wanted to find two.
so I wanted you to recognize that because that's part of the, like when you have a word problem and they just write a whole bunch of stuff and they say, oh, cubic centimeters per second. You want to recognize that that's dv dt. Whereas like inches per second, that would be just like dx dt or dy dt. Area would be square. The ones that you want to remember, dv dt is always something cubed per time.
So if it said 20 centimeters squared, it would be
Yeah, so and dAdt is units squared per time.
Why does it really matter?
That makes a big difference.
No, I mean like when you're. No, I mean, because like your final answer isn't gonna have that.
No, but what I'm saying, what I was trying to explain to you is when you have a word problem, you have to take from the wording
Oh, yeah.
and figure out what were you given. Like
Yeah,
I wouldn't
like-
say this is dx dt. This is a change in volume.
What if you did put dx dt, you'd still be able to get the answer?
You
if you
would,
Like, know what the problem
if
is.
you knew, right? It would still work. You can technically use any variable
Yeah.
you want. Andrew, you had your hand up.
Yeah, when I get this problem on a test and I absolutely can't do anything, how many points will I get for writing dq over dt?
Does that seem?
You know what? Surprisingly, you will get credit just for identifying the information in the problem. So on the AP exam, they will sometimes, just for recognizing the different parts, they'll give you a point.
Circling.
Like DV, like labeling, and plugging it in properly, even if you set up the whole problem wrong. part of it is just understanding the pieces that you have to substitute in. Luke?
Quick question that probably doesn't matter, but does it matter if you use capital A or lowercase r?
It doesn't.
What is this?
Surface area.
Ah,
Okay, so I gave you the formulas in case you don't know them. 4/3 pi r cubed is the volume of a sphere, and 4 pi r squared is the surface area for a sphere.
Wait, the volume is for pi.
This is volume, this is surface area. Okay, so let's actually look at the first one. How fast is the radius increasing when the radius is 4 centimeters? What do you mean it makes no sense? So remember, your sphere, we have, okay, so we have the change in volume. So basically helium is going into this at 20 cubic centimeters per second. So right at 4 centimeters, how fast is the radius changing? So take volume and take d dt of both sides. Okay. On the left side, well, the derivative is just going to be dv dt. What about the right side? Well, 4/3 pi is all just that's just a coefficient. So I'm going to move the 3 to the front, so that will cancel the 3 on the bottom. So we get 4 pi r squared dr dt. Let me just pause there and make sure we're...
You have to memorize the fourth.
No, I'll give you the formulas.
Can you just plug in 20 for DVDT?
why wouldn't you plug in the 4 centimeters in the initial radius?
Okay, why don't I plug in the initial radius? Is the radius constant?
The radius is increasing.
There are no constants in this problem. As the radius, obviously, as the volume is increasing, the radius is increasing. So they're saying right at 4, so let's say we froze it at 4 centimeters. How fast is that radius changing at that moment?
Could you tell me what we're doing?
We just kind of talked about what these were. Like, in terms of recognition.
Needs to use the volume or the surface area.
Okay, so in part A, because we were provided with dv dt, that's what we started with. Okay, so in other words, I can't use surface area formula when I was provided with the change in volume.
Oh, okay.
But what if I gave you the change in the surface area? Then we would go with that problem.
Can you go up for 1 second?
So you can go ahead and plug in now if you want. So here, dv dt was 20. 4 pi times 4 squared dr dt. So basically, what do we have? 16 times 4, so 60, so 20 over 64 pi. Make sure you put parentheses around it when you divide.
Should we solve it?
Yeah, just figure out what that is to 3 decimal places. These will all be rounded to 3 decimal.
1.4.
009?
Should I be in radians or degrees?
It doesn't matter.
Oh, then I got 0.09 there.
Okay, so how fast is the radius changing? The radius is changing at what? 0.099. What are the units?
Centimeters.
Did you put parentheses around the,
Did not, that makes sense. Centimeters.
'cause then it's gonna, centimeters per second.
Oh,
So as the volume is changing at 20 cubic centimeters per second, the radius is changing at basically a 1/10 of a centimeter per second.
Can you round to 10? Or is that?
3 decimal places for calc. Okay, how fast is the surface area increasing? So now just write down the formula. What's the surface area? 4 pi r squared. Okay, now what do I wanna do? I don't have anything constant. So I wanna take d dt of both sides. Okay, on the left side, what do we have? ds dt. On the right side, I have 8 pi r dr dt. Now I'm trying to solve.
Does it equal the same thing?
Right, well, we found dr dt from the previous
Oh, wonderful.
problem.
How fast is rate is first? Okay,
Okay, so
that's solving.
we found dr dt equals 0.099 from above. That was only because it said at 4 centimeters. If it said 3 centimeters, we'd have to go back and solve that problem with 3. But I intentionally gave you the same answer.
Will
So,
you do
eh,
that for
yeah,
us all the time?
yeah. I won't trick you and give you a different one. So go ahead and solve that. Or I will.
2.4.
Oh,
Is that close?
how about 10?
I don't know, I just make my random numbers, that's sound good.
10 is the answer.
I like that number.
Are you sure it's not 9.9?
One sec, I need
It
to
might be
copy.
9.95.
Can you go up the side, I need to copy this down.
Yeah.
Okay, so I used the answer in my calculator, so the pi's cancel, and then you're just left with 10. If you, I didn't use 0.099, I used the number, the actual number that was in my calculator. Then it comes out exactly. So,
But should we put 10 or just remove the?
oh, the surface area, oops. The surface area is changing. 10 square centimeters per second. That was kind of messy.
On the test, would you accept 9.95 to be?
Yeah. Because if you use 0.099, then that's okay. Oh. Okay.
I feel like no one's here.
You done?
Doesn't feel empty.
Alright, time
That
to
was
read
it for-
the sticky notes.
You want to read your sticky notes?
Oh, yeah, please read.
Can I read them in like a wait, can I read them in like a really intense voice?
But the,
Oh, you know what? I have them over in there.
Let's put on.
Please, can I read my sticky notes first?
What?
Let's put on pause before we do